The strongest material in the universe, and it's not diamond. What if I told you there's something 10 billion times stronger than steel? Hidden deep inside some of the most extreme objects in space? Scientists call it nuclear pasta, and it might just be the strongest material in existence. But what is it? Where does it come from? And why would it explode like a nuclear bomb if you brought it to Earth? Let's get into the madness. When people think of the hardest material on Earth, diamond is usually the first thing that comes to mind. And for good reason. It's incredibly tough. We use it to cut through steel, polish other gems, and even in high-tech applications like industrial drills and lasers. But here's the thing. Just because something is the hardest natural material on Earth doesn't mean it's the strongest thing in the universe. Out in space, where the laws of physics push materials to their absolute limits, diamond doesn't even come close to being the toughest stuff around. There are materials out there that make diamond look fragile, and one of them is so ridiculously strong that scientists say it's 10 billion times stronger than steel. That's not an exaggeration, that's actual research. It's called nuclear pasta, and it forms inside neutron stars, some of the densest, most extreme objects in the universe. This stuff is so tough that if you somehow tried to break a piece of it, it would take forces beyond anything we could generate on Earth. But strength isn't as simple as being unbreakable. A wrecking ball and a spider web both have strength, just in different ways. So what kind of strength are we talking about here? There's more than one way to measure it. Some materials can handle extreme pulling forces without snapping. That's tensile strength. Others can take an enormous amount of weight pressing down on them. That's compressive strength. And then there's shear strength, which is all about resisting forces that try to tear a material apart from different angles. Steel, for example, stretches under tension but doesn't easily snap. Concrete holds up entire skyscrapers, but the right kind of pressure can crack it. Diamond? It's nearly impossible to scratch, but one wrong hit and it shatters. Nuclear pasta, though, is in a class of its own. It doesn't just resist breaking. It takes forces beyond anything we can create to even put a dent in it. But strength like that doesn't just happen. It takes an environment so extreme that even atoms are forced into strange new forms. And the only place in the universe where that happens? Somewhere in deep space. But nuclear pasta doesn't just float around in space waiting to be discovered. It forms in one of the most extreme environments in the universe, the heart of a neutron star. And neutron stars? They're born from destruction. When a massive star, about 10 to 30 times bigger than our sun, reaches the end of its life, it goes out with a bang. A supernova explosion rips through space, ejecting most of the star's outer layers in a violent burst of energy. But the core? That part doesn't get to escape. Instead, it collapses under its own gravity, squeezing down with unimaginable force.
We know of about 2,000 neutron stars in our galaxy, but there probably are many, many more. I'm talking about tens of millions in the Milky Way alone.
The result is a neutron star, an object with more mass than the sun, but packed into a space no bigger than a city. That's like cramming a mountain into a sugar cube. The pressure inside is so intense that protons and electrons are crushed together, forming a dense sea of neutrons. But it doesn't stop there. The extreme conditions force matter into bizarre shapes that don't exist anywhere else in the universe. If you were to somehow look inside a neutron star, which, for the record, would be impossible without getting obliterated, you wouldn't find anything like the solid surfaces we're used to. Instead, deep beneath the surface, atomic nuclei are being crushed together under insane pressure, forcing them into shapes that don't exist anywhere else. Scientists call this bizarre substance nuclear pasta, and yes, it's named after actual pasta because of the way it forms. The structure isn't random. The immense gravity inside a neutron star forces nuclear matter into distinct patterns. Sometimes, the material stretches into long, thin tubes resembling strands of spaghetti. Other times it flattens into stacked layers that look like lasagna sheets. In even denser areas, it clumps into round clusters, similar to gnocchi. The names might sound playful, but the physics behind them is anything but. At first, this might seem like some weird cosmic coincidence, but these shapes actually maximize strength at the atomic level. The forces acting on nuclear pasta are so extreme that atoms can't just sit in the normal solid structure. They're rearranged into formations that can resist breaking in ways no earthly material ever could. This isn't just an interesting scientific oddity. Nuclear pasta is the strongest known material in the universe. But saying it's strong doesn't really do it justice. Just how tough is it? The numbers are almost impossible to believe. Scientists estimate it's 10 billion times stronger than steel, a number so ridiculous it almost doesn't seem real. For comparison, diamond is one of the hardest materials on Earth. It can withstand extreme pressure, but it's brittle. Hit it the right way and it cracks. Graphene is incredibly strong for its size, but it's still possible to tear it apart. Carbon nanotubes have insane tensile strength, but they're microscopic, so they're not exactly building block material. Even wurtzite boron nitride, which is technically harder than diamond, doesn't come close to nuclear pasta. This stuff outperforms all of them. It doesn't just resist breaking, it practically refuses to. The forces inside a neutron star twist and crush everything into these bizarre pasta-like shapes, and once they form, they're nearly indestructible. If you could somehow pull a piece out and put it in a lab, no machine on Earth would be strong enough to break it. But there's a reason nothing on Earth comes close to the strength of nuclear pasta. It's not just about how it's shaped, it's about the fundamental forces that hold it together. This stuff exists in a place where the rules of matter get pushed to their absolute limits. First, there's the strong nuclear force, the same force that holds protons and neutrons together inside an atom's nucleus. Normally, this force only works at the subatomic level, but inside a neutron star, the pressure is so intense that it binds massive structures of nuclear material together, making them almost impossible to break apart. Then there's the gravity, and not just any gravity. A neutron star's gravitational pull is so intense that it crushes matter tighter than anywhere else in the universe. It's like squeezing a mountain into the size of a pebble. This extreme pressure forces nuclear pasta into dense, rigid shapes that maximize resistance to breaking in ways no earthly material can. The result? A substance so strong that even the insane forces inside a neutron star struggle to break it. If nuclear pasta were somehow placed on Earth, it wouldn't just be tough, it would be completely indestructible. But here's the thing, it can't exist outside of a neutron star. The moment it's removed from that crushing pressure, it won't just lose its strength. It would explode with more energy than a nuclear bomb. So, nuclear pasta is a material that physically shouldn't exist anywhere else. But let's just say, somehow, you manage to grab a chunk of nuclear pasta from a neutron star and bring it back to Earth. What would happen? Well, the second it arrives, it won't just sit there. It will explode. Not just with a small pop, but with the force of a nuclear bomb. And that's not a theory, that's just physics. Nuclear pasta only holds its structure because of the extreme gravitational pressure inside a neutron star. That pressure is what keeps it stable. The moment you take it out of that environment, the forces holding it together collapse, and the energy trapped inside is violently released. It's the same reason you can't bring a piece of a star back to Earth. The conditions that create these materials only exist in space, and without them, they break apart in ways we can't even contain. This is why nuclear pasta isn't just the strongest material in the universe, it's a material that can't survive anywhere else. But just because we can't physically bring it here doesn't mean we can't study it. Scientists have found other ways to understand nuclear pasta without ever touching it. It's not like scientists can just grab a telescope and spot it. Instead, they rely on some of the most powerful tools we have: supercomputer simulations and gravitational waves. Supercomputers allow researchers to recreate the extreme conditions inside neutron stars using complex physics models. By simulating the crushing gravity and intense nuclear forces, scientists can predict how matter behaves at these extreme densities. And every time they run these simulations, nuclear pasta keeps showing up. The model suggests that as neutron stars cool and their matter settles, nuclear pasta naturally forms deep beneath the surface. But it's not just a digital experiment. There's real, indirect evidence from space. Neutron stars don't just sit there. They spin rapidly, collide, and send ripples through the fabric of space-time. These ripples, called gravitational waves, can be detected on Earth. When scientists analyze these waves, they sometimes find small irregularities, disruptions that might be caused by the strange structure of nuclear pasta beneath the neutron star's surface. This kind of research isn't just about finding weird materials. It helps scientists understand neutron stars themselves. Studying nuclear pasta gives us clues about how neutron stars evolve, and even what might happen when two of them collide. We may never hold nuclear pasta in our hands, but the more we study it, the more we know about the most extreme objects in the universe. One of the wildest things about them is their insanely powerful magnetic fields. Some neutron stars, called magnetars, have fields so strong they can rip apart atoms and cause entire planets to shift. Their magnetic strength is 1 trillion times stronger than Earth's, and scientists still don't fully understand what makes them so extreme. But neutron stars don't just sit there warping space and pulling in matter. They also help create the building blocks of planets. When two neutron stars collide, the explosion is so intense that it forges heavy elements like gold and platinum. These elements don't just stay in space. Over billions of years they mix into forming planets, meaning the gold in your ring or necklace may have started its journey in a neutron star merger billions of years ago. And right beneath the surface of these stars, nuclear pasta. It's not just some bizarre material. It actually plays a role in shaping how neutron stars behave. It affects how they cool, how their crusts crack under pressure, and even how they send out gravitational waves across space. Nuclear pasta might be the strongest material we know of, but it's not the only strange thing lurking in the universe. There are even weirder substances out there, pushing the boundaries of what we think is possible. Take neutronium, for example. This is pure neutron matter found at the core of neutron stars, where gravity is so extreme that even atoms collapse. There are no protons, no electrons, just neutrons packed together in a way that would be impossible anywhere else. It's so dense that a sugar cube-sized chunk of it would weigh 1 billion tons on Earth. Then there's strange matter, a hypothetical material made of something even smaller than neutrons, quarks. Scientists think it might exist inside even more extreme stars, called quark stars. Some theories even suggest that strange matter could be the most stable form of matter in the universe, meaning anything it touches might turn into strange matter too. If that's true, it could explain some of the most mysterious objects in space. These materials challenge everything we know about physics, and with new discoveries happening all the time, who knows what else is waiting to be found? So, what are your thoughts on this? Let us know in the comments down below.